In our last segment, we looked at what happened when we combined together a weak acid and its conjugate weak base. And what we determined was that together they formed a buffer, and that the pH of that buffer, if the two components were mixed in equal amounts, would be close to the pKa of the acid. Now, you might have been thinking to yourself at that moment, well, that's nice, but why should I care? Well, now let's look at why buffers are so useful and why it's so important that we're able to handle the math related to them. To do that, we're going to be working on this problem right here. In this case, we're talking about what would happen if we added a drop of a drop of 1 molar HCl. That drop we're going to approximate as about 0.05 milliliters. What would happen if we added that into 10 milliliters of solution, either water or the buffer solution that we made last time? And just a reminder, that buffer solution is 0.025 molar acetic acid, 0.025 molar sodium acetate, and it has a pKa of 4.76. So this is going to take a little bit. We're going to divide this into two videos. In the first video, I want to look at what would happen if we were to add to water. And in the second case, I want to look at what would happen if we added to the buffer. So let's get started with the water example. So in thinking about the water, we're going to be working with, once added together, 10.05 milliliters, which, based on the number of significant figures we have here, is small enough that we can effectively neglect the added volume that was brought in from our droplet. So this is the kind of math that we were doing last semester. It's a dilution problem. So if we had 0.05, and we'll give it one more significant figure here, milliliters of our solution, for every 1,000 milliliters, we get 1 liter, and for every 1 liter, we get 1 mole of HCl. Now we can do one more thing, because we know this is a strong acid. We can say for every 1 mole of HCl, we're going to get 1 mole of H plus floating around in solution. So that means that we're talking about having 5 times 10 to the negative 5 moles of H plus, and that is going to be in 10 milliliters of solution. And again, we should take this over to convert our milliliters into liters so that we can now determine our new concentration. So that's 10 to the 1. This is 10 to the 3. Subtracting those, that gives us 10 to the 2. That is subtracting the exponents, which means that we're talking about a 5 times 10 to the negative 3 molar H plus solution. Last but not least, we should probably know the pH. That's typically the way we like to discuss the impact of, for instance, adding an acid to a solution. So let's put in our significant figures here. Don't want to get too sloppy. That's going to give us a pH of 2.30. What does that mean? Well, that means that even adding 1 drop of HCl to 10 milliliters of water brought the pH from 7, where it started, all the way down to 2.3. That's an enormous swing. In particular, that's a large enough swing that if, for instance, you had some organism living in that water, it would probably not survive it. Keep in mind as well that when water sits out in our Earth atmosphere, it will slowly dissolve carbon dioxide from the atmosphere, which will form carbonic acid. So over time, even water left completely alone, if it's uncapped, will slowly find its pH going down as it dissolves CO2. What that means is that if we want the pH of a solution to remain stable, we're going to need to do something a little bit more to keep it that way. What we're going to see in the next segment, or the next half of this segment, is that a buffer can prevent that pH change.